In this section, I want to talk about how digital images work in the computer. So here I've got an example image of some yellow flowers, and what we're going to see is that this looks like sort of an organic, rounded whole thing. In the computer, it's going to come down to really just a lot of little numbers. So how does that work? So what I want to do is focus on this upper left flower here. You'll see there's a little green area with a little thing in the middle. So if I zoom in by a factor of 10 on just that square, it looks like this. So what you see is that the image is made of these little square things. So these are called pixels. So each pixel is square. They're quite small, so there's not an exact number for it, but maybe 100 pixels per inch. And each pixel shows just a single color. So it's just locked as the square of a single color. And what's funny is if you look at it here, it looks kind of very artificial and hard-edged. But because the pixels are so small, when you look at it here in the original image, it just looks right. The pixels are small enough that you don't see those little hard edges. So this is what an image looks like if you sort of zoom in and see the parts. If you want to think about how many pixels there are in an image, it's just a question of multiplication. So if I had an image that was 800 pixels wide by 600 pixels high, it's just a question of multiplying. So multiply those two, and that's 480,000 pixels. You may have heard the term megapixel. It's commonly used for computers and cameras and things. So a megapixel is 1,000,000 pixels. So my 800 by 600 image, 480,000, well, that's about a half a megapixel, roughly speaking. So that's not a very big image by modern standards. A digital camera today, even on a phone, usually would produce an image on the order of 5 megapixels, 10 megapixels, maybe 20 megapixels. That would be a pretty big image. All right, so let's see how this thing works. So I've made just to make it a little more crisp, I made this diagram. So if I have an image, I can think of it really as this grid of pixels. So each pixel is a square, and it's just showing a single color. Now, we're going to have an addressing scheme to sort of identify each pixel as opposed to all the others. So the way that works is we have a set of x numbers along the top here. So 0 is the far left, and then it goes up, going to the right. And then the y direction is done in a sort of a unique way. So 0 is the top row, and then the y numbers read down. And that's just historically how images are numbered in the computer. So I could just do some simple examples. So for example, the absolute upper left pixel is at 0, 0, or x equals 0, y equals 0, I could say. The pixel 1 to its right, so this pixel here, is at x equals 1, y equals 0. And a lot of times if I say the coordinate, the convention is to just say the x number and then the y number. So I would say this is 1, 0. And let's say this pixel over here, well, you can kind of read up. It's at x equals 4, y equals 2, or I could just say 4, 2. Now, in reality, we're not going to get into a lot of detail of messing around with these x, y numbers to identify specific pixels. You just need to appreciate that there is this scheme. So even if we had 10 million pixels, any particular pixel has some x, y number that addresses it versus all the other pixels. So the question is, well, I've got these pixels. How do I encode what the color is of any particular pixel? And so to talk about that, I'm going to make a brief historical side trip. So Newton had this famous experiment in the 1600s where he had which I've reproduced here, a prism, which is just a triangular piece of glass. And here, white sunlight is coming in the left-hand side, and the prism splits it into the spectrum of colors here, which I just projected onto a white piece of paper. So what this shows is that white light is not some indivisible, pure thing. Instead, it can be separated into these pure constituent colors. And so this is the same thing that you would see with a rainbow. So the colors are actually in a continuous spectrum, but Newton identified certain ones, gave them words. So this is the famous sequence where it goes red on the side here, and then orange and yellow and green, and finally blue, indigo, and violet on the far side here. So in the computer, I want to think of these pure colors as kind of a palette. And the scheme we're going to use is to pick actually red, green, and blue out of here and use those as sort of as constituents to build up any other color we might want. Or ultimately you could think of it, here we have white light coming in the left and we get the constituents out here, you can think of it as running it backwards. That if I took the constituent colors and ran them back this way, I could get white light out. And the physics is not exactly the same, but this is a little bit suggestive of how we're going to take the constituents and put them together in the computer. Also, there's kind of a funny thing about indigo here. When Newton named these, right, in between blue and violet, we've got indigo. And it seems like, really, indigo, that like we needed a separate word for that. Couldn't we just call that blue? And it's funny because it shows sort of what it's like to live in the 1600s. Newton was believed in a certain amount of mysticism, things that we think of as not scientific. And at the time, there were 7 known planets, and Newton felt like, well, the number of colors, it should sort of match up the number of planets. And so I think he kind of forced indigo in there just to make the numbers add up. All right, so what I'm going to do is work on this scheme to encode a particular color called the RGB color scheme. RGB stands for red, green, blue. And the way this works, or the question is, I want a way of encoding what each color is inside of my grid there. And so in the RGB scheme, we're going to use pure red, green, and blue lights. And mixing those in different combinations be able to form any kind of color. And rather than try and talk through this, really this just demos very well. So I'm going to go to this RGB Explorer page. And this will allow me to demonstrate how this works. So the way this works is I've got these 3 sliders on the left here. So there's this one controls the red light. And we're going to number these. So when the red is all the way dark, we're going to call that 0. And if I turn it all the way up to maximum, we're going to call that 255. And if you see here at the bottom, actually, it always reads out what the numbers are for the sliders. So I've got a red slider and a green slider for making green light, and a blue slider making blue light. And so the strategy in the RGB scheme is that essentially you have these 3 knobs that I can have. I can vary the brightness of red, green, and blue light. And it turns out you can make any color by combining just the right proportions of red, green, and blue. So I'll show some examples. Well, so obviously if I want to make red, I would just turn red up all the way. And likewise, if I want to make green, I would just turn green up all the way. If you turn it all the way, you get kind of a bright version. If I wanted darker green, well, I can start with green and then just sort of turn it down so that I get darker green and go all this way. Now, really, the left-hand side here, the 0 numbers represents black. So in a sense, what I'm doing is I'm taking green. I'm like, well, I just sort of go closer to black, and that's dark green. So the other end, if I want to make white, this is the case where I take red and I turn it all the way up, and green and blue, and turn them all the way up, and that's how I get white. So all the numbers at 255, that's white, and then turning them all the way down here, all at 0, that's black. So let me show just a few combinations here. I think probably the most interesting one is red plus green. So if I turn red up and I turn green all the way up, what I get is yellow. And if I wanted to make maybe a slightly darker yellow, well, I can keep red and green sort of close to each other, but just turn them both down a little bit towards black, and I get a darker yellow, or we'll go this way, I'll get like an even darker yellow. If I want to make orange, what I'm going to do is I think of orange as being like, well, it's kind of like yellow, but instead of red and green being similar, the red is a little stronger. So I'll have red and green here, and then I'll just turn the red up a little bit, and I'll turn the green down a little bit, and we can get a nice orange there. That's kind of the road cone color, kind of a nice orange. So this sort of just gives you the flavor of how you can, by tweaking things, end up making a lot of different colors. Let's see, there was one other example I wanted to do. Oh yeah, I'll make kind of a light green. So let me show how to make a pastel yellow. So here I've got red and green turned up all the way, so I'm getting this very bright yellow. And so pastel you think of as being kind of more diffuse, more sort of foggy. And so the way to do that is actually I'm going to add in blue. So I'll turn the blue up to about 185 here. And as you can see, well, it's still yellow, but it's kind of pastel foggy. And the way to think about that is like, well, if I had all 3 of these all the way at max, that was white. And so by turning the blue up, I've sort of gone towards white, but instead of just pure white, by having the red and green a little bit of the head of the blue, I end up with this yellow cast. Now, the way this is going to work for this class is I'm not requiring that you have, you can just pull out of the air what the 3 numbers are for any particular color. It's just that you appreciate that there is this basic scheme to make colors just by varying red, green, and blue. Let's see, there was just one other one I want to show. So we did red, green, yellow is important. I'll do the other combinations. So blue plus green at maximum, you see, is kind of a turquoise. Kind of makes sense, sort of a blue-green. And our last combination will be red plus blue. So red plus blue, you get kind of a violet. That kind of makes sense. That is sort of, does seem to be a combination of red and blue. All right, so let me go back here to our images. So we've got this idea that you can take red, green, and blue light and mix them together. And so what that means in terms of the image is that I've got all those pixels. For every pixel is going to have some color, and that color is going to be defined by red, green, blue levels. Or in terms of numbers, what it means is basically every pixel just has 3 numbers. So I could say, well, red is 250 and green is 10 and blue is 240. But I mean, more likely we're just say, oh yeah, that pixel is 250, 10, 40. So we tend to always use the order: the red number, then the green number, then the blue number. So I can sort of refine my diagram here. So here's my grid of pixels. It's making up the image, and we've got the XY like we had before. And now, essentially, what's going on with each one of these pixels is that each one has its own 3 numbers. So maybe this one is 6, 257, i.e., right? So 6 is very low, green, 250 very high, blue, 7 is low, i.e., basically green, right? The green number is very high. And this pixel might be 241, 252, 23. So red and green are very high, blue is very low. It's basically some shade of yellow. I should say that when we take digital images in the real world, right, when I was playing with the sliders, well, I tended to have either 255 or 0. In the real world, you always get some intermediate number like 237 or 26 or whatever, and they're mixed together to make whatever that particular shade is. So this is going to be our kind of working definition of an image for now. So we've got this big grid of pixels. Every pixel each pixel shows one color, and that color is completely captured by just 3 numbers. So kind of stepping back a little bit, we started with this whole image, and I've reduced it to just this grid that has a lot of numbers. And that's actually a very common theme in computer science. You start off with a whole image or a whole sound or a whole encyclopedia or something, which as a human we think of that as sort of this organic whole. In the computer, inevitably, all that data, there's some organizational scheme where it's structured down to just a lot of little numbers. That is how it's going to be represented in the computer. And if we think of an operation on the data, so if I wanted to take an image and maybe make it a little lighter, in the computer we're going to translate that into some operation on the numbers. So for example, for an image, if I wanted to make it a little lighter, like, well, geez, we've got all these red, green, blue numbers. Maybe what I could do is just go through and add 10 to each one. And if you think back to the RGB Explorer, I'm going to shift each one a little bit to the right, just make it a little bit lighter. Anyway, that's going to be a few sections from now, but the general theme that in the computer things are stored as a lot of little numbers, and that's what the computer domain looks like. That is certainly something we'll be seeing a lot more.